So what happens then if you have species or acids within the same groups? We're talking about top to bottom or in a group, not going across like we did before. So here are our examples. Let's look at them. We have HF, HCl, HBr, HI. You remember these. You have an alcohol and you have a sulfide here. So let's look at the pKa's of these. Here's the data. The data tells us from the pK that this has a 3.2. This is a -7. HBr is a -9. HI is a -10. And the pK of the alcohol here is 17. And of course, 10.5 for the sulfide. So what is happening here? How come these become incredibly more acidic, like HI? Look how acidic it is. The lower the pK, the more acidic. So again, the trend here we see is that the increasing acidity but here's the thing. The electronegativity is actually the opposite. So in the electronegativity is the opposite. So this is increasing electronegativity in the opposite way. So what is happening here? How come? So we see an opposite trend here. Why? Well, the reason why is because they have different sizes. If you recall from Gen Chem, the size of the atom increases as you go down the table, the periodic table. So for example, might become like this and that. If that's bigger, we'll make this a little bit bigger for you so you can see it. So the size increases as you go down the table. So when comparing atoms of very different size, the size of the atom is more important than its electronegativity. So keep that in mind. In the element effect, if you are comparing atoms with different sizes, look at the size of the atom rather than the electronegativity. And it's for a simple reason, at least at this level. If you look at the conjugate bases right here, you actually notice that the iodine, the bromide, iodide, the bromide, the chloride, the fluoride are uh, in the sense they are more stable. Okay, if you actually go from the I is most stable, then the Br, then the Cl, then the F. So how come? Here's why. The positive charge or negative charge is stabilized when it's spread over a larger volume. So think about it. Electrons don't like each other. So I is huge. And you have that negative charge in there. I is in the fifth shell. Okay. So here we say valence electrons in fifth shell. If we draw F, it would be this small. Look at that negative charge. It doesn't have enough room, all right, to move around. The valence electrons here, we say, are in the second shell. So, you know, the shell is smaller at the second level than the fifth level. So what information do we need here is that the volume is larger, a lot larger. Second is that the negative charge is spread over a larger volume of space. And I'm going to need more information here, more actually to write a little bit more. So that actually results in what we say the electron density decreasing. So if you have less electron density over a large volume, kind of like pressure, I always think of it, right? Is that if you have pressure decreases if you increase the volume from Boyle's law. So if you compress something, the pressure is going to build up because you're decreasing the space. Versus if you increase the space, the pressure is very low, right? So imagine, think of it that way, is that there's less electron density. Remember from Gen Chem that the larger the volume, the smaller the density will be. And that actually results in increasing the stability of the molecule. And I just want to write one more thing here, is that less electron density equals more stability. And of course, these would be, if they are more stable, then these would be less basic. So these are the element effects.